In this third and final video from section 9.5, we'll look at some patterns and applications of series. So, a pattern. If you have a sigma notation of a constant, there's nowhere to plug the k in, the k value. So from 1 to 5, it's just 3, 5 times. It doesn't change. 5 threes. So in general, if you have a constant, C for a constant, and you have n different terms, each term will just be C. So the answer will just be n times C, 5 times 3. If you go from 1 to 5 and it's just a k, nothing else. So you plug in 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's a nice arithmetic series right there. So we can do 5 over 2, first term, last term, get your answer. In general, you can do n over 2. First term will be just 1. Every single time the first term will be 1 if you start with k equals 1. So assuming that. And the last term will be whatever's on top, which would be n. So n plus 1 over 2. That's a nice little pattern right there when there's just a k. If it's k squared, we have a slightly more difficult pattern. And if it's k to the third power, we have another pattern right here. These patterns can be proven if you use the method of induction, which is what section 9.6 is about. We're not going to prove them here, but just show that for these examples, these formulas work. Plugging in n equals 5 for all the n's, you get something which is equivalent to our answer. These two formulas here do not need to be memorized. They would be given on a quiz. These two formulas you should know how to derive without being given the formula. Here's an example right here of a polynomial, and we're going to find the sum of the series just of 5 different terms. So we could obviously plug in 1 for all the k's, plug in 2 for all the k's, 3, 4, 5, and we could do the work out and we would get our answer. If it was from 1 to 500, that way would be not a good way, but we can do it for 5 terms. In addition, we're going to show that you could divide up this 1 sigma notation into multiple ones for each term, and we could do each term separately. In addition, maybe you remember that we could take a coefficient that has nothing to do with k, and we could drag it outside of the sigma notation. And then we could use our formulas for k to the 3, k squared, n plus 1, 2n plus 1 over 6, for k, and for a constant, n times a constant. And we could total those up and get our answer. This would be really preferable, again, if that was 500, this way would take the same amount of time. This way would take much, much more. One application that you can use series for is financing and money. So for instance, a problem that you've probably seen before, you put $100 in the bank at 3% APR, that's annual percent rate, and so the interest rate that you would get annualized. But it's compounded monthly, and we're going to have the money in there for 10 years. Here's the formula that you've probably seen. The principal is $100. The annual interest rate is 3% as a decimal, compounded 12 times a year, and then 12 times our 10 years. And we would end up with $134.94. All right, here's a variation of the problem. What if I don't just put $100 in the bank one time and walk away for 10 years, but I put $100 every single month into an annuity? Now, an annuity would just be something like an IRA account or a 403b account, something that I won't take out until after I've retired. So I just keep putting it in there every month, another $100 automatically, and I do this for 10 years. And it's compounded monthly at 3%. So that first $100 that I put in there is going to get a lot of interest on it, where that last $100 that I put in on the last month isn't going to get much interest on it. Okay, so I'm going to initially make the assumption that this $100 gets put in at the first of each month. We'll look at that assumption in a minute. So the very last time I put the $100 in, when there's only 1 month left before my 10 years is over, that $100 will earn 1 month of interest. And that 1 month, the amount of interest will be the 3% annual divided by 12, because a twelfth of that. The second to the last time I put the money into the annuity, it will earn 2 months of interest, being put in on the first of the month, have 2 full months, that $100, 2 full months at this interest rate, etc., etc. The very first time I put the $100 in, at the beginning of the 10-year period, it will be just like this problem here. It will earn, for all of those time periods, its interest rate. It'll just be sitting there. But now I have all of these $100 contributions that I need to combine together to find out the total amount. And this is a geometric series. Imagine this is my first term right here. And then to get from this term to this term, I will multiply by some common ratio. And that is in fact how I get from one term to the next, is each time multiplying by this common ratio. This is my formula for a finite geometric series with 120 terms. The R value is here. The A1 value is this whole thing. And I can see how much money I will have after the 10 years. Okay, if the money was put in on the last of the month, then that very last contribution would earn no interest. I brought it to the bank, I gave them $100, and then it's, oh, by the way, I want all my money back. So I won't have earned any interest there. The second to the last contribution, I'll earn 1 month of interest, etc., etc. So you can see that first $100, I put it at the very end of the month, so there's 119 months left. My R is the same, my A is just slightly different, but I still have 120 terms in the summation. N is still 120, there's 120 pieces there. This will be my noon total, and that is a difference of 0.25%, which as far as planning for retirement is really minimal. The point being that if you have a question like this on a quiz, whether you make the first assumption or the last, it's really not going to matter. You got it correct either way. Here's a last issue though. In this problem, we're using the letter R in 2 different capacities. Here, R stands for the annual interest rate, the APR. Down here, R stands for the common ratio. Now that we're talking about geometric series, there's an R in that formula. This R is not the interest rate, it's the common ratio. So we have to be really careful about which R we're talking about. And even if you have to put APR right here and right here, that is probably preferable so you don't mix them up. All right, so in this problem here, imagine that someday you go to the bank, you get a $150,000 30-year mortgage so you can buy a house. And that mortgage is given to you at a 4.5% APR, compounded monthly. What will be your monthly payment? Well, first of all, this is a very simplified problem. When you get a mortgage from the bank, the APR is only part of the thing because there's fees, administrative costs, lawyers, things, and so there's something called an effective annual percent rate, but we're not going to talk about that. Okay, so let's look at how we would solve this problem right here. All right, in this problem here, looking at it from the bank's perspective, they have made a one-time given you $150,000. That's their principal in you, and they have an annual interest rate and a number of times that's going to be compounded. And so they have an expectation of how much money they will have at the end of this 30-year period from this one-time putting of money into you. You, on the other hand, are going to be paying monthly. Instead of paying into an annuity every month and earning interest on that annuity, you are going to be paying into the bank and deducting the interest that you owe. So it's just like the last problem we did. In this case, A1, that is my monthly payment. That's the first payment that I owe, and then interest from there. So you can see we have all the numbers. We know all the numbers from the bank's point of view, and we know almost all the numbers from your point of view. And so we can solve for the monthly payment. Also notice that when the bank gives you a $150,000 loan over 30 years, you end up paying back about 3.5 times that amount, including interest charges. All right, the last thing I said isn't actually true, as we're going to find out. You don't actually end up paying this amount of money back to the bank for your $150,000 loan. Let's see why. What if you say, you know what, I think I can pay more than $760 a month. I got a pretty good job. So what if I pay this mortgage back in 20 years instead of 30 years? How much would I save? So the bank would now adjust their years from 30 to 20. And you would adjust your years as well. But everything else is the same exact thing. And this time we'd find out that you would have to pay $948.98 per month. And so if you can afford that, you will do it for much fewer months because you'll only be doing it for 20 years. So your savings would be the original amount times 12 months times 30 years minus the new amount times 12 months times 20 years. And then you can see that this is actually what you would be paying the bank for your $150,000 loan for the privilege of borrowing it so you can have a house now. You'd be paying back not quite double of what it was. But you would save $45,000, almost $46,000, if you could pay it back quicker. This is why people maybe initially can only afford this much, but then they get a better job, and so they decide to refinance and reduce the payback period. Or maybe the APR reduces to like 3.5%, and they refinance, because that would be another important way that you could reduce the remaining amount that you owe to the bank. All right, this last slide is just a little bit of theory. So you have the bank's point of view, and this principle that they've given you, the mortgage, is what the bank calls present value. That's what the money is worth to them today. The entire side here is called the future value, what the money is worth in the future. We're going to replace this APR over K with just the letter I for monthly interest. And we're going to replace A1 with PMT, which stands for your monthly payment. Then we have turned the equation into this. Notice that in the new denominator, the ones cancel out. At this point, we can divide both sides by this factor right here to cross cancel. And on the other side over here, we can do 1 divided by that minus this divided by that. And of course, if you have 1 over something to a power, you can bring the denominator up, but the power becomes negative. And then we can multiply top and bottom by -1 to make the I be positive, but to make this be a positive 1 and this be a minus factor if we distribute in -1. And what we get is the accepted formula for a mortgage amount and a monthly payment. And this formula is actually in section 3.6 of our pre-calc book. They just give it to you. But it comes from geometric series, monthly payments, on a lump sum investment made on your behalf called a mortgage from the bank.